So when we started talking about intermolecular forces, we talked about molecules that have a dipole, or a polar molecule, where there's a net charge on one side of the molecule. When we put a lot of these molecules together, we get intermolecular interactions between the positive side, the hydrogen, and the negative side, the oxygen. You put a lot of these molecules together, and you can see the effects of these intermolecular forces, creating a structure. Here's our negative oxygens, our positive hydrogens, and an interaction between them. This is easy to understand for polar molecules. But what happens with nonpolar molecules? We know that nonpolar molecules can be liquids. If we think of some large hydrocarbons, it's just hydrogen and carbon, and the molecule is symmetrical, so they're not polar, but we know that they can become liquids. We know that even some small nonpolar molecules can become liquids under certain circumstances, so under high pressure or very low temperature. And we think of carbon dioxide and nitrogen gas, both of which we can compress to form a liquid. How can this happen? Let's look at an example of a single atom. Let's look at helium. Helium has 2 protons and 2 electrons. And we usually imagine these electrons circling the nucleus and staying far apart from each other because electrons would repel each other. But because these electrons are always in motion, at an instant in time, it's possible that they would be on the same side of the atom. And at another instant in time, it's possible that they would be on a different side of the atom. Keep in mind that this would just be a very brief, instantaneous interaction. But at these moments, there would be a net pull in this direction on this atom, or in this direction on a different atom. When we add these all up, all of these instants, it's going to cancel out so that we wouldn't have a net dipole, but we might have an instantaneous dipole. So here's an illustration of an instantaneous dipole. So here's our helium atoms. We have no polarization, the electrons are evenly distributed, but in an instant in time, more of the electrons are on one side of the helium atom, resulting in a negative charge on this side of the atom and a partial positive charge on this side. What will happen is this will cause an effect on the neighboring atom. And now this positive charge will attract the negative charges on the neighboring atom, and we'll have an induced dipole. So we have an instantaneous dipole just because the electrons are always in motion. At a snapshot in time it can happen. And then we have an induced dipole on the neighboring atom. This example is with a single atom, helium, but the same thing can happen for a molecule. So here's an example with hydrogen. Hydrogen is nonpolar. We have the same atom. There's no net dipole. But in an instant in time, we can have a net negative on one side, a net positive on the other side. Instantaneous dipole induces a dipole on the next molecule. This is what can lead to intermolecular forces in nonpolar molecules. These intermolecular forces on nonpolar molecules can have many different names. Instantaneous dipole is my favorite because it explains to me what's going on. But you will also hear these called dispersion forces, van der Waals forces, London forces, London dispersion forces, and induced dipoles. It's important that you're familiar with all of these terms because you will see and hear them used interchangeably. You need to know that these are all the same thing. Instantaneous dipoles occur in all molecules, polar or nonpolar, but they are the most important intermolecular force for nonpolar molecules. These instantaneous dipoles become more important and more significant the larger the molecule gets. And this makes sense because as a molecule becomes larger, the electrons get farther and farther away from the nucleus. So if we imagine our nucleus and we have our shells of electrons around it, in our first shell we could have 2 electrons, and our second shell we could have 8. These innermost electrons are feeling the full effect of the nucleus, pulling it in towards the nucleus. As we move farther away from the nucleus, we get some repulsions between the electrons that are closer to the nucleus. The farther away from the nucleus we get, the more polarizable our atom or electron can be. So we're more polarizable. And what this means is that it's easier to distort the electron cloud. So it's easier to distort the electron cloud. It's easier to get an atom or a molecule that looks more like this and less perfectly symmetrical and spherical. So if we can distort the electron cloud more easily, then the intermolecular forces are going to be stronger, particularly the dispersion forces will be stronger for a larger molecule.